Okay, so welcome to this video. In this video what we're going to be talking about is the remainder theorem. Okay, and we're going to be studying the remainder theorem in the context of the complex numbers. Okay, so in the context of polynomials with coefficients in the complex numbers. Okay, it can be generalized beyond that. Okay, but we're just going to study it in the context of the complex numbers. Okay, right. So firstly, let's start off by discussing what the remainder theorem actually says. Okay, so the remainder theorem, as we're going to study it, is all about polynomials with coefficients in the complex numbers. Okay, now the polynomials that are interesting in the remainder theorem are polynomials of degree 1 or greater. Okay, so not just constant polynomials and not the zero polynomial. Okay, some polynomial with an actual x term in it, basically. Okay, and let's say that our polynomial has degree n, so I might write our polynomial out as p little n here, just meaning some coefficient, times x to the power of n plus pn minus 1 times x to the power of n minus 1 plus all the way down to plus p0, basically. Okay, and these are all just coefficients, so the pi's are all just coefficients which are in the complex numbers, basically. So all of these are just the coefficients here. Okay, and they're all just complex numbers. Okay, right, so the degree of this polynomial is little n here, where little n is some natural number, basically. Okay, so that can be written del p, meaning the degree of p is equal to little n here. Okay, right, so now what is the remainder theorem then? Well, what the remainder theorem says is that if you take any, let's call it alpha, which is an element of the complex numbers, so take any complex number you like, basically, okay, and we're representing this complex number as alpha, then basically what you can do is you can factor out x minus alpha from this polynomial here. Okay, so you can rewrite this polynomial p of x as x minus alpha, this linear term here, times some other polynomial which we'll call q of x. Okay, and q of x here is a polynomial of degree 1 less than the polynomial of p, so it will have degree n minus 1, basically. So I'll just write that del q, the degree of q, will be equal to n minus 1. And the reason we call it q is for quotient, basically. Okay, it's the thing that you've got left over once you've divided this polynomial by x minus alpha, basically. Once you've factored out x minus alpha from our polynomial p of x. Okay, I think I'll just colour code px in as well in orange there. Okay, now that's not the finished theorem, by the way. Okay, then you have to have plus some remainder, which we'll call r. Okay, and this is now just a constant term, so r is just a complex number. Okay, the complex number that makes this work. Okay, now I can actually get you a very explicit formula for what r is, and this is how I can simply from this get you a simple formula for what r is, because if I substitute in the complex number alpha, okay, into both sides of this equation, okay, if I substitute it in to the left hand side, what I'll get is the polynomial p evaluated at this complex number alpha. Okay, so that's just substituting alpha in here. And then if I substitute it in on the right hand side, I'll get alpha minus alpha here, which will give me 0. And then 0 times whatever q of alpha is equal to. I don't care what q of alpha is equal to, because anything times 0 in the complex numbers is just 0. So that now just leaves this constant term r, which is unaffected by what alpha you put in to the x variable, basically. Okay, so that means now that this remainder term r must just equal the value of the polynomial p evaluated at the constant alpha, basically. So just stick in this alpha complex number into your polynomial, okay, your p of x. So put in x is equal to alpha, you can work out some complex number for p of alpha, okay, and that's going to be this remainder term, basically. So there is your explicit formula for what this r value is in terms of alpha, basically. Okay, right, so that's the remainder theorem, that basically you can take any polynomial, and this polynomial needs to have a degree either 1 or bigger, okay? So we're not interested in polynomials that are constant polynomials. Obviously, if you've got a constant polynomial, then you can't do this. You can't factor out x minus alpha from a constant polynomial, okay? But a degree 1 polynomial or higher, you can do this with, basically, okay? Right, so I'll just put that in. The degree of p needs to be greater than or equal to 1. Okay, so I'm not interested in the constant polynomials, and I'm certainly not interested in the 0 polynomial. Okay, right. So you can rewrite any polynomial of degree greater than or equal to 1 in this form, x minus alpha, where alpha is any complex number you can dream up, times some new polynomial, q of x, which will have degree 1 less than the polynomial p of x. Okay, and that's really why this condition is necessary, because obviously if this wasn't true, then we'd have a problem with the degree of q. Okay, and then plus some correcting term, some remainder term, which is just a complex number, basically. And we've got this explicit formula for what that complex number is. So let's now prove that you can rewrite your polynomial like this, or really derive, because this is a very intuitive thing to be able to show. So I would really call this a derivation rather than a proof. Okay, right, so how can we show this then? Okay, so let's just bring down our polynomial back down here. So p of x is equal to pn x to the power of n plus pn minus 1 x to the power of n minus 1 plus all the way down to plus p naught. Okay, now what we would really like to be able to do is rewrite this in terms of powers of x minus alpha. If I could rewrite this polynomial in terms of powers of x minus alpha rather than powers of x, then I could just pull out x minus alpha from this. Okay, and that's the motivation for what I'm about to do. Okay, so what I am going to do is I'm going to say, let's rewrite this polynomial here in terms of a new variable y, which is going to equal x minus alpha. Okay, and then we'll substitute in x minus alpha later on. So what does this mean? That x is just going to equal y plus alpha. So this is the great idea. Substitute in x is equal to y plus alpha into this polynomial. Okay, expand that polynomial out to get it in terms of y, and then just remember that y is now equal to x minus alpha, so then we've got a polynomial in terms of x minus alpha, basically, which is equivalent to this polynomial. Okay, so this is the way that we're going to manage to rewrite this polynomial in terms of powers of x minus alpha. So let me show you what I'm going to now do. So I'm going to substitute in x is equal to y plus alpha. I'm just rewriting this polynomial in terms of a different variable y, and then later on I'm going to reverse this silly changing to a different variable so that I'll bring it back in terms of the variable x. Okay, right, so just temporarily what I'm going to do is I'm going to substitute in x is equal to y plus alpha. So I'll get pn times, whoops, not like that. Okay, so substituting in y is, x is equal to y plus alpha. We'll get y plus alpha to the power of n plus pn minus 1 x, oh sorry, I'm not thinking straight here, y plus alpha to the power of n minus 1, and then we'll go all the way down to plus p naught, like so. So that's utterly correct. All I'm doing is rewriting it in terms of another variable. Okay, if we were just to return back in y is equal to x minus alpha into here, we'd get our polynomial back again. Okay, right. Then what I can do is I can expand all of these out. Okay, so I can expand them all out in terms using the binomial expansion, basically. Okay, and then I can rewrite this entire polynomial, and I will once again get a polynomial in terms of powers of y this time. Okay, but it will still be a polynomial of degree little n here, because this is going to be our term which gives the highest power of y, basically, and the highest power of y it will give is y to the power of n. So this will still be a polynomial in terms of y of degree n, basically. So what we will end up with then is a polynomial, and I'm going to denote the coefficients a. Okay, so we'll have an y to the power of n plus an minus 1 y to the power of n minus 1 plus all the way down to a naught. Now I'm not working out what these terms actually are. You could in principle write what each of these coefficients are in terms of the coefficients of p, in terms of the p coefficients here basically. Okay, it's a job and a half basically. What I'm doing here is I'm simplifying it down. I'm not going to go through the technicalities of actually working out what these are and getting explicit formulas for what they are in terms of p. I'm saying if you had some specific values for what the p values here are, you could then do this. You could expand it out like so, okay, and you could then get a polynomial like this in terms of powers of y, basically, okay, where these a's are some complex numbers. Okay, so I haven't found you explicit formulas for what they actually are. You could do it. You could get explicit formulas for what they are in terms of these coefficients and in terms of alpha, okay, but we're not going to do that. What I'm saying is that you could do it. Okay, right, now all you have to do is replace back y is equal to x minus alpha, and what you'll get is an x minus alpha to the power of n plus an minus 1 x minus alpha to the power of n minus 1 plus all the way down to a0, like so. Okay, and now it's really, really simple. Okay, all you need to do is factor out x minus alpha from all of the terms which have an x minus alpha. Okay, so this is the only term right down here that doesn't actually have an x minus alpha. The plus a naught is our constant term, and that's the only term that doesn't have a power of x minus alpha, basically. Okay, all the other terms, right down to plus a1 times x minus alpha here, do have an x minus alpha to some power, basically. Okay, and what you can now do is pull out x minus alpha from all of those, and what you'll get is x minus alpha times, big brackets, an times x minus alpha to the power of n minus 1 plus an minus 1 times x minus alpha to the power of n minus 2. So this is what corresponds to this term here. This corresponds to this term. Now I'll just colour code it up. Okay, so this is this term with x minus alpha pulled out of it. Okay, this term is over here. Okay, again with an x minus alpha pulled out of it, and then we'll go right down to this term here, and we'll pull out that x minus alpha, and we'll end up with just plus a1. Okay, and then outside of the great brackets we'll have plus a naught here. Okay, now all we need to do is expand this great polynomial out, okay, using again the binomial expansion, and what will you end up with now? What's the highest power of x you're going to end up with here? It's going to be x to the power of n minus 1 from this term here. So you will now end up with a polynomial q of x, which will have degree n minus 1, so degree of q will equal n minus 1. Okay, which is exactly what I said we were going to do. So now what I have got you is I have rewritten your polynomial p of x in terms of x minus alpha times q of x, okay, which is a polynomial of degree 1 less than the degree of the polynomial p of x, plus some constant term, a0, which is just some complex number. Okay, and we know exactly what that complex number will be. It will actually be the polynomial, the original polynomial we had here, evaluated at your value alpha, basically. Okay, right, so there is your derivation of the remainder theorem, basically. Okay, what we'll do in the next video is we will look at what the fundamental theorem of algebra says, and we will use the remainder theorem to then get this other, slightly more developed version of the fundamental theorem of algebra, which is often just quoted as being the fundamental theorem of algebra, although it isn't actually the fundamental theorem of algebra. It's sort of a corollary of the fundamental theorem of algebra. Okay, so we'll do that in the next video.